Have you ever looked up at the night sky at all those stars and wondered what else is out there? Well, imagine finding out that almost everything, maybe 68% of the entire universe, is invisible, undetectable.
And not just invisible, but actively driving the whole show.
Exactly. We're talking about dark energy. It's a huge mystery, and today we're diving deep into what we know, and maybe what we don't, about this dominant force.
Yeah, and as we look at the source material, what's really striking is how this unseen stuff isn't just sitting there. It's actively shaping the universe's expansion, its whole destiny. It has profound implications.
Profound feels like an understatement. So, okay, something this huge. How did we even figure out it exists? Where does the story start?
Well, the groundwork was laid back in the early 20th century. That's when we first realized the universe wasn't static, it was actually expanding.
Right, Hubble's discovery, already a pretty big deal. The universe is getting bigger.
A massive deal.
Yeah.
But then things got really weird in 1998. There was this astonishing realization.
Okay, what happened?
Astronomers were looking at very distant type Ia supernovae. These are exploding stars, incredibly useful because they have a known brightness, like standard candles across cosmic distances.
Right, they let us measure how far away things are and how fast they're moving away.
Precisely. And the data from these supernovae showed something completely unexpected. The expansion wasn't slowing down, as everyone thought gravity would make it do.
It wasn't.
No, it was accelerating, speeding up.
Wait, accelerating. So getting faster over time. That sounds backwards, like something's pushing it.
Exactly like something's pushing it. This meant some unknown force, some kind of energy inherent in space itself, was overcoming gravity on the largest scales. They called it dark energy.
And it's not just a tiny push, is it? The numbers are staggering.
Oh, they really are.
Yeah.
When you look at the cosmic inventory based on things like the cosmic microwave background radiation, galaxy surveys, the picture is just mind-bending.
Get this. Dark energy makes up about 68% of the total energy density of the universe.
68%.
Then there's dark matter, another mystery, at about 27%.
Which leaves
Less than 5% for everything else. Everything we see. Stars, planets, gas, dust, us, all of it. Just a tiny fraction.
It's incredibly humbling, isn't it? We're focusing on this tiny sliver of reality we can actually interact with, while the vast majority is this dark stuff.
So what is this dark energy then? If it's 68% of everything, surely we know something.
Well, that's the billion-dollar question, isn't it? Despite its dominance, its true nature is still very much unknown. The leading theory connects back to Einstein, actually.
Oh, how so?
He introduced something called the cosmological constant into his equations, initially for the wrong reasons, he thought. But it represents the possibility that empty space itself has an inherent energy, a vacuum energy.
So empty space isn't really empty, it has energy.
That's the idea. This vacuum energy would have a constant density everywhere and would cause space to expand. It fits the observations quite well, mostly.
Mostly. So there are other ideas floating around? What did the sources say?
Oh, yes. It's not a closed case. Some physicists propose a dynamic field, something called quintessence, which could change in strength over space and time, unlike a constant.
Okay, so it wouldn't be fixed.
Exactly. And then there are more, well, radical ideas. Maybe our understanding of gravity itself is incomplete on these cosmic scales. Maybe general relativity needs modifying.
Wow. So we're potentially looking at needing new physics. Let's go back to how it works, though. You said it pushes space apart. How? Gravity pulls, right?
Right. Normal matter and energy cause attractive gravity. But dark energy is different. It exerts negative pressure.
Negative pressure? What does that even mean?
Think of it like tension in the fabric of space itself. Instead of pulling things together, this negative pressure results in a repulsive gravitational effect. It pushes space apart.
So it's like anti-gravity, in a sense.
In a way, yes. That's a good way to think about it. And because it seems to be a property of space itself, as space expands, you get more space and this more dark energy effect, driving even faster expansion.
And that leads to some pretty bleak long-term forecasts, doesn't it?
It certainly can. If dark energy remains constant or strengthens, the accelerating expansion will eventually push galaxies so far apart they disappear beyond each other's observable horizon.
Yep.
It points towards a potential big freeze or heat death.
A cold, dark, empty future. Grim. Okay, let's quickly clear something up. Dark energy, dark matter, they sound similar, both dark. How are they different?
Crucial distinction. Yes, they're both invisible to us directly, hence dark, but they do opposite things. Dark matter pulls. Its gravity holds galaxies and galaxy clusters together, Without it, galaxies would fly apart.
Okay, so dark matter is like cosmic glue.
A good analogy. Dark energy, on the other hand, pushes. It drives the accelerated expansion of space itself.
Glue versus anti-glue.
Maybe. And their distribution is different, too. Dark matter clumps up where regular matter is, in galaxies and halos around them. Dark energy seems to be smooth, uniformly spread throughout all of space.
Totally different jobs, totally different distributions. Got it. So putting it all together, this dominant accelerating force, what does it ultimately mean for the future? What's the universe's fate?
Well, as we touched on, it really hinges on the true nature of dark energy, which we still don't fully understand.
Right.
If dark energy is truly constant, like Einstein's cosmological constant suggests, the universe will expand forever, getting colder, darker, emptier. Galaxies receding faster and faster.
Big freeze scenario.
Yes. If dark energy somehow increases in strength over time, that quintessence idea, maybe you could get a big rip.
A big rip. That sounds violent.
It would be. Expansion accelerates so much it eventually overcomes all other forces, tearing apart galaxy clusters, then galaxies, stars, planets, even atoms themselves.
Yikes. Okay, what if it weakens?
If it weakens or reverses, then gravity could eventually win out. The expansion would slow, stop, and reverse into a big crunch, collapsing back in on itself.
So freeze, rip, or crunch. Which way is the evidence pointing now?
Currently. The observational evidence strongly favors the constant dark energy model. So eternal expansion seems the most likely scenario based on what we see today.
It's just amazing to realize that the main driver of the universe's entire future is this thing we can't see, can't touch, and barely understand. It's, mind-bending.
It really is. And maybe that's the thought to leave you with. How does knowing this change your perspective? Knowing that the vast, vast majority of the cosmos, the stuff dictating our ultimate fate, is utterly alien to our everyday experience. It really highlights how much more there might be out there still completely unknown.